Hello everyone, and welcome to Cotalks. In this session, we are going to talk about machine learning on Kubernetes and how we can build a platform for our data scientists to make them reach their goals. My name is Farhad. I'm a tech lead at adjoe. I've been with adjoe since the beginning, and during these 6 years, we built a lot of infrastructure that I will show you a bit of it. And I've been in the industry as well since 12 years. adjoe is a scale-up working in ad industry, and we have unique advertisement and monetization platforms for our partners and publishers and clients. We are operating in more than 150 countries. We receive a lot of data from our partners, and we train machine learning models to be able to deliver the best ads for our users. And we receive more than 5 billion API calls daily. So you can imagine that this is like a huge load and traffic coming in. A little bit about the business, just so we understand why we need this platform. So we have two sides of the business. The first side is the advertiser side, meaning that these are the apps that want to acquire users and they want to advertise their app. And we have the monetizer side, which these are the apps that have a lot of users and they're well known and they want to monetize their users. And we have a lot of machine learning algorithms and also machine learning models that help us to connect these two sides smartly together. So in this talk, we are going to discuss an overview of our infrastructure, the current infrastructure that we have. Then we will discuss why we are going to build this platform in another AWS account. Later, we will go over how do we leverage Spot instances in order to save costs. And in the end, we will discuss GPU workloads on Kubernetes, and we will look at the next steps and what we are looking for after this. So, an overview of infrastructure. At a glance, it could be like looking a little bit complicated, but you need to remember that we didn't build this overnight. It's been like 6 years that we've been working on this infrastructure that can handle that 5 billion requests per day. If I want to go through a really overview of this on a high level, we have the client-facing side. This is where all the API calls from our users come in. And we have application load balancer acting as an API gateway and sends the API calls to the correct microservice on the backend system. If the request is for a static resource, of course, we have our CDN, CloudFront. It will immediately answer that request. Our microservices are developed mostly in Go, and we use different container orchestration platforms in order to manage them. We use EKS, Kubernetes on AWS, ECS, and both of these container orchestration platforms are backed by EC2 instances. Even in production, we leverage Spot instances, meaning that, okay, even our production workload is mostly running on Spot. And in order to do that, we use Carpenter, an open source project. We will discuss it in its own slides later. We have auto-scaling on container level and also on the EC2 instance level in order to scale out and scale in depending on the traffic. And the microservices are designed as stateless microservices. That means that, okay, we need to store the state somewhere. That's why we have this wide variety of databases at the bottom. We have columnar databases, row-based databases, NoSQL databases, Redis clusters for caching and coordination, and so on and so forth. To the right, we have the logging stack. We use Elasticsearch. And also we use an open source project called OpenObserve. It's developed in Rust. And we are also one of the contributors to this project. This project helps us to have longer retention for our logs, store them as Parquet files in our S3 compliant buckets, meaning that, okay, our costs will be reduced and we can retain the logs longer. And also, this enables us to be able to query these logs even with query engines like Athena and PrestoDB. We ship the logs with FluentBit. That's, yeah, we just ship the logs Fluent with, and we move to monitoring side, classic CloudWatch on AWS. For AWS services, we use Prometheus and Grafana for monitoring Kubernetes clusters and all the open source projects that we deploy there. We use Sentry for application critical incident management, and we have an incident management platform that aggregates everything for us called the Squadcast. These microservices are designed via event-driven design, meaning that, okay, we need an event buster. We use SQS and SNS for communication between these microservices. We used to use Kinesis Firehose for a streaming platform. Now we are migrating to Kafka, which we deploy on our own Kubernetes cluster. And we have Flink, which is a real-time stream processing platform. We have different Flink jobs that hook to different Kafka topics and process the messages there. For the data lake, we use S3 to store the Parquet files, Glue for the meta store, and to be able to use Glue crawlers to crawl the data. And we used to use EMR for our Spark applications, which is an AWS platform. And we still use Athena for querying the data lake. The far left side, the machine learning platform, this one we are going to build together today in this session. Please note that the whole production environment was previously in the same AWS account, which we are going to change. We are going to detach that part and bring it into its own AWS account, and later on we will discuss why we want to do this. So let's talk a little bit about the pain points that we had. We used to run GPU workloads manually on the GPU instances, GPU EC2 instances on AWS. This comes with some problems. The first one is your GPU is never fully utilized because your data scientists are exploring, they're using this instance, and each instance is assigned to one data scientist. He's on lunchtime, for example, or whatever, or he's developing some code and the training is not going on. So you will pay for what you're not using. This we want to fix. And of course, it was on-demand instances. So we pay the full price. The second thing is the EMR. We were using Spark workloads. The problem with EMR is that you need to bring up the clusters. It takes like, I don't know, 15, 20 minutes for an EMR cluster to come up. And you need to manually add and remove nodes unless you're using the hosted EMR version or EMR on Kubernetes. And of course, you will have also on-demand instances for the master nodes and for the core nodes. And also with these platforms, for example, SageMaker, EMR comes the platform cost that would be on top for you on AWS. Let's talk about what do we need for this environment. What do our data scientists need? We need to be able to use a wide variety of instances, meaning that we have the GPU workload, CPU workload, memory optimized workload. We need to have different node pools, which we discuss later, to enable our data scientists to run their workload efficiently. They will have variety of dependencies, meaning that each application, each data scientist that is working on different applications, they need their own dependencies. For example, some of them have GPU workload, they need to use different drivers, different frameworks, Tensor Flow, PyTorch, and etc. Or they need, for example, a Spark workloads, different frameworks again. So they need to be able to package their dependencies efficiently. And of course, we talked about we want another AWS account, meaning that, okay, they need to be able to access different data lakes in order to train their models in different AWS accounts. That's what we are going to solve as well. Our end goal is to build something like this. So we will still have a client-facing side. This will enable our data scientists to be able to connect to different web interfaces for different open source projects that you see on the left side on machine learning and also on the right side monitoring and logging. We will use Amazon RDS in order to be able to back some metadata of different open source projects that I will mention later on. It will be a really tiny cluster because it would have like a very small load there. We will use S3 as our object store. OpenObserve and FluentBit we discussed before. We will use them for logging, and we will use Grafana and Prometheus for the monitoring. But of course, the most interesting part is the compute side and the machine learning side. For the compute side, we use Kubernetes cluster backed by spot EC2 instances mostly, and we will leverage Carpenter in order to add and remove those nodes. For the machine learning platform, we will have Airflow to be able to schedule our jobs and DAGs. We will use Spark operator in order to be able to use Spark submits and run Spark jobs on Kubernetes. We will have JupyterHub as our notebook server, as well as Zeppelin, in order to be able to develop on this platform. And we will use MLflow in order to manage our experiments and as our machine learning model artifact store. And all of this will be in the new AWS account that we will create. As you saw, we mentioned a lot of open source technologies. So why at adjoe do we want to use open source technologies, and why do we want to be cloud agnostic? So you all know that open source technologies enable you to do more with less. What does it mean? It means that a lot of engineers across the globe are working on really interesting projects, innovative projects that are packaged, and they are also production ready, meaning that when you leverage them, you can do a lot more with less. At adjoe, we have this mindset that we don't only want to use these projects, but we also want to give back to the community. That's why we maintain some of these projects, and whatever project that we use, whenever we see that we need a feature or there is a bug, we try to fix it and contribute to these projects as well. Examples could be Druid operator. I don't know if you guys know about the Druid database. It's an open source columnar database that we also use at adjoe. Druid operator helps you to be able to deploy this database on Kubernetes efficiently. And we are one of the maintainers of this Druid operator. OpenObserve, I already mentioned that we contribute, and so on and so forth. And we want to reduce our vendor lock-in, of course. When we began at the beginning, we were a very small startup, 4 or 5 people sitting there. Of course, we use a lot of AWS services, and I really recommend for you to use one of the scale-ups, hyperscalers, sorry, to be able to start your startup if you're doing your own, and to be able to get up and running super quick. But after a while, you need to change when your business grows, and then this happens. You have some vendor lock-in, and you start reducing it and removing it. And that's what we are doing with open source projects and Kubernetes. Let's talk a little bit about why do we want to do it in a new AWS account. It's a best practice by AWS. Whenever you have a new project, new environment, it's better be isolated in new environment. But what do we get? We get more security and easier access management. You can have the cost overview at a glance for different accounts that you have. For example, you will have your management account at the top. You will have different sub-accounts, for example, your production environment for project A, production environment for project B, and your, for example, machine learning platform, which is another production environment. These are sub-accounts, yeah? You will get workload isolation. For example, if something goes wrong in my machine learning platform, my production workload won't be affected. Super clear and easy. And of course, you will have flexibility of experimentation, meaning that you can give more access to your developers because they are contained in their own account and they will run what they build. But there will be challenges for you as well. So managing this access between these AWS accounts is a little bit difficult, meaning that, okay, for example, for our platform that we are building for this machine learning platform, we want to give access to our data scientists to be able to access data lakes on different AWS accounts from different projects. Yeah. The second thing is that you will have also problem with the credential lifetimes. On AWS, it's really AWS specific, so we will use role chaining to be able to access from, for example, Airflow worker, some data lake on another account. And it will limit our credentials lifetime to 1 hour. And usually these jobs run more than 1 hour, so it will be like failing after 1 hour. So you need to use the correct libraries, correct SDKs to be able to refresh these credentials. That's how we solve it. And whenever those libraries are not existing, you need to build your own. This would be a problem. For the cross-account access, for infrastructure as a code, we use Terraform, and for the cross-account access, we developed a new module for ourselves that makes our lives easier, and we use that module everywhere. We define what kind of access from which account we want to give to this platform, and then we will apply the Terraform, and we will have all the accesses in place. Let's talk a little bit about Spot instances and how to use them to save costs. So I want to talk a little bit about Carpenter. I won't go deep into every point of this diagram. It's a little bit complicated, but you can use Carpenter to be able to add Spot instances to your EKS clusters or your Kubernetes clusters and leverage Spot instances. How does it work? You need to deploy the Carpenter pods there. Then you will use some custom resources like node pools and node classes that you define the pools of nodes, and with the node class you define, for example, which AMI you want to use, which security group you want to connect to this node pool. And Carpenter will always monitor the pending pods, the ones that are marked as unschedulable, and it will try based on the node pools, taints and tolerations that are there to assign new nodes to the cluster and remove the nodes from the cluster when they're not needed. How does it help us? First of all, we will save costs by using Spot instances. Secondly, it would be a dynamic and elastic environment, meaning that, for example, when I launch as a data scientist, a Spark job that I need, 120 workers there will be 120 nodes added to the cluster immediately. And when my job is done, these nodes will scale in and they will be gone. That means that I pay for what I use. Moving on a little bit, I talked about taints and tolerations for you guys to understand how it works. Just a refresher, we will have a worker here. It has a taint GPU equals true colon no schedule, meaning that any pods that don't have this toleration for this taint, they won't be scheduled on this node. So that's how we manage what workload to run on which node pool, which are here. So let's discuss the node pools that we need in this platform. So the first one is the default node pool, 100% Spot instances. Why do we need this? We want to run OpenObserve, for example, Prometheus, Grafana, any other pods that are for our infrastructure. We will run on the default node pool. The second one is the on-demand node pool, 100% on demand. Why do we need on-demand node pools? Because some applications should not be interrupted. Meaning, for example, when you launch a Spark job on Kubernetes using Spark operator, you will have a Spark driver, which will come and manage all the workers for that job. Means that if this driver, if because of Spot interruptions get interrupted, the whole job will fail. We don't want to have that. We want to make it stable. That's why we run the Spark drivers on, for example, this node pool. Another example would be the notebook servers that we will later on discuss, that for the Jupyter notebook. So we don't want our data scientists to be interrupted when they are developing something by Spot interruptions. Next, we will have high and mid-spec node pools, 100% Spot. These node pools are the ones that actually do the job. Meaning that, okay, for example, when you run a Spark job on Kubernetes, all the workers will be run on Spot on this type of node pools. And last but not least, I said that we have GPU workloads to train, and we use Spot instances in the GPU node pool. We chose JupyterHub because of really nice features that it has. I want to explain like 1-2 features here that why we chose JupyterHub. For example, in JupyterHub, you can have different profiles, meaning that the data scientists, based on what they want to do, they can choose one of these profiles. For example, you want to use GPU training, you will use GPU high spec, for example, that we create here. It will have the tolerations for that GPU node pool that I described before, to be able to launch on that notebook. Another thing was that we discussed we want to have flexibility of the dependencies, drivers, and so on and so forth. And how do we enable our data scientists to manage their own dependencies on this environment? So we have a Git repo for our Docker files. We will have different folders for different applications, for different users. And each user will have its own Docker files, dependencies, and also the libraries that they want there. And they will build that Docker file using the CI/CD pipelines that we created for them. And the pipeline will push the image to our container repository, which in this case is ECR. And then the data scientists want to use that image, meaning that, okay, we will leverage kubespawner from JupyterHub. We have a custom script there based on the user. It knows that which image it needs to pull for the user. Meaning that, okay, whenever you choose a profile based on your user, you get your own dependencies also. Super flexible. All right. Let's a little bit talk about syncing the code and why do we need to sync the code from some Git repository. We have different applications. I mentioned that we have Airflow and we have Airflow DAGs. You need to bring this code from somewhere to the Airflow pods to be able to available and to be able to run. We have a Git repository that we store these DAGs there. The data scientists work on it. We have like separate branches, of course, but in this case, we have the develop branch using an open source project called GitSync, which is running as a sidecar on Airflow containers. It will pull the branches that we configure. In this case, for example, for a production environment, it will pull the main branch, and for developer environment, it will sync for staging environment, it will sync the develop branch, meaning that the data scientists can test even their DAGs by just pushing to different branches. Another use case is Jupyter notebooks. So we also have another repository that the data scientists commit their notebooks. This is like the work that they did over time and they're for different projects. And they need these notebooks to be available at all times in their JupyterHub notebook server. That's why we will use also GitSync there, this open source project, to be able to pull the correct notebooks in the correct pods. Let's discuss a little bit GPU workloads and understand how are we planning to run the GPU workloads on Kubernetes. For that, we need to understand what do we need to be able to add a GPU to a container. So we will use AMIs from AWS called EKS optimized AMIs, always in the EKS cluster, but in this case, we will use with GPU support. What does it add? It will have an NVIDIA driver. By the way, we are using mostly NVIDIA, but you can use also AMD GPUs based on what your data scientists need. But in this session, we will talk about NVIDIA because we are using NVIDIA right now. So you will have NVIDIA driver there, a container runtime, and the wrapper for the container runtime from NVIDIA. What does this wrapper do? It enables you to be able to connect a physical GPU to a container. And of course, the whole package is an EKS optimized AMI with GPU support. But this is just to connect to a container. Now I want to use this in Kubernetes. So I need a little bit more than that. So Kubernetes gives provides a framework called device plugin. Using this framework with different vendors, implement their own device plugin, and this device plugin can do various stuff. In our case, the device plugin manages the GPUs and connects them to the pods now. So before we could connect it to a container on the container runtime, but Kubernetes needs to be aware of that. And that's where the NVIDIA device plugin comes into play. We will deploy NVIDIA device plugin as a daemon set on the GPU workloads, on the GPU work node pool that we described before. And what is inside the application containers for the GPU workload is defined here. For example, we will have the mapped NVIDIA driver, CUDA toolkit, deep layering libraries. Your framework could be PyTorch, I don't know, Tensor Flow, anything else, and your application code, of course. But up to this point, we are training on a single instance, meaning that the users are launching notebooks or data scientists, and they have one server that they're training on with one GPU. Now we want to go one step further and enable them to be able to train on multiple worker nodes, meaning distributed training. Why do we need that? Because some of these trainings take a lot of time, and we want to make it faster by leveraging multiple GPUs and not just scaling them up, but scaling them out. For that, we use Kubeflow's training operator. This operator you can deploy on Kubernetes standalone, so you don't need really the full package of Kubeflow to be able to use this. And using the custom resources, you can just employ those custom resources and run your job on different nodes. It also supports many APIs and many frameworks like PyTorch, Tensor Flow, XGBoost, and so on and so forth. Feel free to check. It's open source on GitHub. The project is really nice. Let's talk a little bit about the next steps, what we are looking for next in this environment. So I mentioned that we use EKS optimized AMIs to connect to our EKS cluster. But in the GPU, we had the GPU support, meaning that, okay, we had something packaged by AWS, and we are using that to be able to run this. There is another way to do this. NVIDIA provides a GPU operator. This enables you to use the same AMI that you're using for example, CPU and memory optimized node pools. Meaning that, for example, this is like just an EKS optimized AMI with no GPU support, but this operator will bring all the dependencies that you have, and it can upgrade those dependencies for you. That means that you will have less management overhead. How does it look like? Is that you have your GPU, you will have your AMI, which is like the bottom part, and the green part is what the operator will manage, meaning that it will bring for you the device plugin, the drivers, the NVIDIA runtime, and also an added thing that we didn't have before, NVIDIA GPU monitoring. I mentioned that some of our GPUs are not utilized as well. Something that we are looking forward to is to be able to share these GPUs between these different workloads. So there are different ways to do this. The first one is a concurrent way of doing things, meaning that, okay, we do the time slicing. The second one is MPS, multi-process service. CUDA provides this, and it's parallel. Usually, NVIDIA suggests that this is good for the batch workload that doesn't utilize a lot of GPU, meaning that, okay, you can run multiple of these batch workloads on the same GPU on Kubernetes using this multi-process service and share your GPU. And the last one, the MIG, or multi-instance GPU, is the most sophisticated one. You need a GPU which is like very new and has these capabilities, and you can run quality of service workload on this with this sharing scenario. What does it mean? It means that you can break down one GPU that supports MIG into up to seven sub GPUs and assign them each to one pod. But they cannot also interfere with other workload, meaning that they are all isolated, meaning that they cannot burst into their whole processing unit or cache and interrupt other workloads. So you will have your quality of service. This is best when you have a GPU inference workload and you want to have a quality of service, as well as you want to utilize your whole GPU. So let's discuss a little bit of the results. We monitored our costs between the two environments. We were able to achieve around 38% of cost reduction because of all the stuff that we mentioned. For example, using spot instances, scaling down whenever the nodes are not needed, and also not paying application platform fees on AWS. Our flexibility is increased because the data scientists can easier manage their platform. Everything is automated. There are different pipelines. And we have enhanced security and isolation because we migrated to a new AWS account. Some resources. You can always check our engineering blog. We usually post there frequently about the projects that we are working on and our learnings. If you're interested in the overview of infrastructure that I mentioned in the beginning, I did a deep dive last year in Code Talks. It's called Scalable by Design. You can check it out on YouTube. The link would be there if you're interested in the whole infrastructure and why we are using different services and what kind of migrations we are doing. And yeah, that's it. Thank you.